Hello, my name is Gas, and today I'd like to present to you from 9 sources. The task reads: using a laser beam passing through a thin layer about 200 micrometers of soy sauce, the thermal lens effect can be observed. Investigate this phenomenon. Here you can see a picture of the cross-section of our laser array, where on the left the excitation laser is turned on, and on the right the excitation laser is turned on. Note that the array cross-section clearly widens or loses intensity. This indicates that the thermal lens is actually some kind of dispersive lens. But before we take a look at how this phenomenon works qualitatively, I'd first like to show you my experimental configuration, and afterwards we'll have a look at a quantitative theoretical model for this phenomenon. We'll finally investigate the effect of some parameters of the focal length of the lens, but let's start with the experimental setup. My experiment setup therefore mainly consisted of a probe laser, which you can see here, which produces a coherent light which passed through all the setup, an excitation laser, which was mainly there to include the thermal lens. We also used a converging lens in order to reproducibly create the tail of the probe laser beam right there, where we could now work this. So then a cell was placed between the converging lens and the gray filter, and the gray filter itself was used to reduce the intensity of the probe laser such that it could be measured with our CCD camera right here. So we are able to measure the relative intensity changes due to the lens. The sample cell was then placed in the distance D1 before the converging lens, and the distance D2 before the gray filter, before the CCD plate. Note that this distance D2 in my real experiments was really larger than this. It was about 3 to 4 meters, but for demonstration purposes I've shifted it together. This will become important later. So now to the ray profile. We first have our excitation beam intersecting the sample right here to induce the thermal lens. And we also have our probe laser, which passed through the same point in the sample and was there to measure the optic effect. We can then take a look at the sample itself. Now, the task makes a clear statement, therefore, where we should use a thin layer, about 200 micrometers of soy sauce. And this was created experimentally by taking two microscopic plates of 300 micrometer thickness and two other ones which were thinner in between. The resulting gap was then filled by soy sauce using the capillary effect. Now, for the microscopic plates itself, there were several thicknesses available, and by taking multiple of them, we were able to reproduce sample thicknesses quite reproducibly and vary our sample thickness. So, to continue, we have to choose the laser, so the excitation beam and the probe laser. And therefore, we take a look at the absorption spectrum, which has been measured using an ocean optic spectrum. Here we can see the relative absorption coefficient kappa over the wavelength of the laser. And it's quite intuitive that you want to have a probe laser do not give as much intensity to the sample, and therefore we take 632.8 nanometers, which is a helium neon laser. So note that this has 1 milliwatt, and therefore it was mainly to study the optics, whereas our excitation laser has 80 milliwatts and was at a lower wavelength of about 530 nanometers, and it was there to induce the thermal lens. This helped us to independently study the optical and thermal effects of the lens by deactivating or activating the excitation laser. Now, we also want to understand how this phenomenon works qualitatively, and therefore we take a look at the radial profile of the temperature distribution. Here in the middle we have a wave pattern through it, and if you now write down a linearized model of the variation of the refractive index, we can see that for high temperatures we get a low refractive index, which means that the wave propagates faster, and for the opposite case, exactly the opposite. And this means that the slow waves at the wall of this sample are slower with respect to those in the middle, and therefore we have an effectively bigger phase shift. And from this phase shift, we can now look at the propagation of those waves, and when they interfere at the detector, we can see the characteristic interference pattern, and this widens when our excitation laser is turned off, and we therefore have this temperature gradient. Now we have this phase shift due to the local variation of the refractive index due to temperature, and we want to also account for it quantitatively. Therefore, we have to account for the temperature distribution, and in order to do that, we need to have some material parameters of the soy sauce. Here you can see that we've measured the absorption coefficient of the soy sauce in dependency of the volume fraction. And we can see for 0, this means that pure water, we have the absorption of water, whereas for 1, which is pure soy sauce, we have the absorption of the soy sauce. Writing down Lambert-Beer's law, we can see for this exponential factor linear increase. So this means that our absorption coefficient increases linearly with our soy sauce concentration. These were the values we found, therefore, but there are also other important material characteristics, such as the density, which was found to be slightly bigger than that of water, and the thermal conductivity, which is available in literature. We then used calorimetry to determine our specific heat capacity, and this was slightly lower than this of water, but nevertheless we determined it to be this value. Now we can take a look at this linearized model for the refractive index, where the slope is given in the literature. We can assume then radial symmetry of the problem and write down our two-dimensional coordinates, and then we can also write down the two-dimensional heat equation of solids. Note that D denotes the thermal diffusivity, and Qin is the static heat flux in the sample by the excitation laser. Now, this can be solved with the boundary conditions of zero temperature gradients at the beginning, and also zero temperature gradients at the infinite distance to the center for infinite times. We arrive at the following solution, which is given in literature, and therefore can timely animate this, where we can see that this temperature gradient, which is the reason for the phenomenon, establishes fairly quickly, so the thermal lens goes into a steady state quite quickly. But from this temperature distribution, we have to now account for the phase shift, and we therefore write down the difference of, effectively the difference of the way the path through the liquid follows, and then plug in our solution for the temperature distribution into this refractive index. We then arrive at the this is theta and denotes all material properties, and we now account for the phase shift. Now, we need for the intensity profile, we use the Fresnel diffraction approximation went to the far field, where you can see the incoming Gaussian beam right here, and which is this phase shifted with the phase shift I've calculated just a moment earlier. This can be evaluated numerically, and by looking at the intensity distributions we measured at our detector, we can arrive at quite some good experimental agreement. Now note that this cross-section widens, and if you take a look, we can define a beam radius when the intensity is dropped to 1 over e squared of the original intensity, which is consistent with literature. Now the beam cross-section widens when our excitation laser is turned on, and this will be investigated quantitatively in detail yet. We therefore take a look at how the beam propagates in a little bit more detail, where we can see the tail of the beam right here, as I've mentioned, and after it passed the sample without a thermal lens, it arrived like here, and after it passed the sample with the thermal lens, it arrived like here. This linear propagation can be measured experimentally by shifting the camera on the z-axis, and it's now intuitive to define the intersection with this line and the zero or the optical axis right here, and the distance from this to the axis of the sample at the focal length of the lens. In literature for our theory, there's a derivation available which gives us this quite easy or simple trend in order to predict the focal length of the thermal. Now, we can now start making some variations on this focal length, where we can see here the quite intuitive parameter of the excitation beam power. Note that when the excitation beam power is high, it's quite intuitive that the temperature gradient gets also high. Therefore, the relative intensity or the cross-section change of the laser gets high. This can be seen in this diagram from this axis, and if we take a look at the lower laser powers, we can also see that our focal length gets very small, and this means very big, and this means that our lens is effectively quite weak. Now, if you see, look at the formula, we also have this kappa-c, which has to be determined experimentally a moment earlier, and we found the linear relation. We can now use this linear relation to plot our focal length of the focal length, as we defined earlier, over the volume fraction of soy sauce, where we diluted the soy sauce by taking a pipette and adding water to the soy sauce. This allowed us to use the linear relation obtained, and therefore obtain the focal length of the beaver, where it's quite similar to the plot shown a moment ago. For a large volume fraction of soy sauce, we get a higher absorptivity, and therefore the temperature gradient gets larger, whereas for a small volume fraction, we get a low absorptivity, and therefore focal length tends to go to infinity, which means that the lens is really, really weak. Finally, we've discussed about the time it takes for the lens to go into a steady state, where we found that in our temperature distribution, the gradient of the final gradient of the temperature distribution establishes fairly quickly. And this can be seen in our experiment also, because if you take a look, after about 2 seconds, we don't have any variation larger than 10% of our final focal length, which is reached for infinite time scales. This was also the region where the experiments presented earlier were carried out, but using a video camera at 30 fps and evaluating every first picture, I think, we can also determine the time-dependent focal length of this lens, and by using an additional term or additional factor in the theory, where the characteristics highly scale for the thermal final equilibrium of a soy sauce comes in again. Also, we get some quite quantitative agreement within our experiment and our theory. Now, to summarize what I've did so far. In the task, it says that the thermal lens effect can be observed. And we've done that by giving you a qualitative explanation of the thermal lens effect, where we found that a relative phase shift with respect to the center takes place, and therefore there's interference at the detector plane. And then we went for the thermal part of this effect by calculating the time response temperature distribution in our sample, and for the lens effect by defining a focal length as such that our beam, after it passed the sample, passes this zero axis right here. This focal length of the sample could then be investigated, or its dependency to several parameters could then be investigated experimentally, and we found that with our theoretical approach of a Fresnel diffraction model, we can have quite some good theoretical agreement with respect to time resolved measurements of the focal length for given initial parameters. For the laser power, where we found that a large laser power induces a large heat gradient, and finally also for the concentration of the soy sauce, where we measured our absorption coefficient experimentally and found what's quite intuitive, that for larger concentrations of soy sauce, also the phase shift gets bigger due to a high absorption in the liquid. Therefore, less intensity leaving the liquid on the opposite side. Thank you for your attention.
Right, thank you very much. And so we are moving on to questions from the opponent.
So I'd first like to ask, how did you measure the absorption coefficient of your soy sauce?
So there's a spectrometer. I've used the ocean blue model, and then you take the soy sauce into cuvette and put this cuvette into the spectrometer, and by taking a pipette, which was resolvable to, I think, 1.5 times 10 to the minus 6 liter, so it was quite precise volume determination. I could dilute this soy sauce in the cuvette and then determine the spectrum.
How did you experimentally determine your focal length, the change in focal length?
So, as you see in my setup, I had the sample right here and the camera right here, and I could shift the camera on this axis, and then.
Did you manually shift the camera by yourself?
Yes, but there was there's a fixation on the camera on the axis, and on the axis there was a precise scale, since the axis is made for such optical experiments.
So how did you consider, on your graphs, you considered error bars, how did you determine them?
So the error bars, the main statistical errors, were conducted the experiment multiple times, and therefore I could see maybe a few pixels where the cross-section widened.
Alright, that's fine, thank you. So on slide 5, what was the gap on slide 5? Between your thermal length,
yes.
How much was your soy sauces? Was it 200 microns?
I could use 200 microns, and I have used it, but I can also use 100 or 150 or 300 microns.
So did you use 200 microns? Or
yes, I've used 200 microns.
Did you approximate the thermal lens created as a thin lens?
Not really, because I've taken all optical effects.
Okay, that's fine, thank you. And also,
what do you mean this simplification for the focal length right here? Because there is a thin lens arising due to a quadratic temperature.
That's not fine. So how did you vary the power of your laser?
Sorry?
Did you have multiple lasers?
Yes, I had multiple lasers. There was transmission filters which allowed only a part of the intensity to pass through, and I've just put them in front of my excitation laser to get half of the intensity.
Thank you very much. You've got 3 minutes of preparation time.
An overview of the presentation. So the overall presentation, the theory, the experiments, results, and points of discussion that we'll bring up later for the soy sauce experiment. So some theory, some strengths of this experiment was the mathematical model used by the reporter to describe the beam profile and how the Gaussian beam propagates, and it's used, and that gives an explanation to the Gaussian beam profile that results in the thermal lens effect. Also a mathematical relationship which described the focal length in terms of the relevant parameters of the soy sauce, which is relevant to the experimental setup, and that came back later. But I think areas of improvement that were required in the theory section is highlighting some of the assumptions and the equations and derivations, as a lot of the equations were taken from literature, meaning there are some assumptions made within these equations, and a more intuitive understanding of the phenomenon, going a little bit deeper into why the thermal lens is created as an intuitive explanation. So, in terms of the experiment, the experimental apparatus was quite good. It was all set up on a one-axis platform where the camera was set up at one end, and there's a probably excitation laser. That allows for the experiment multiple parameters to be changed for the experiment, so the excitation beam can be changed, and that allows for relationships to be changed within the experiment. However, areas for improvement, what I think for the experiment was the experiment, the laser itself was in fact not perpendicular to the actual the soy sauce, meaning that could have potentially affect the actual gaseous beam profile incident on that lens, and that could come back later, which will be brought up in the discussion on how it could affect. And also, the results were highlighted the mix between the experimental and as well as theoretical relationships and how they came together and they matched. So that was quite good to see how the trend lines were fitting, and that, and I think that was quite good what the reporter was able to do. However, some of the equations use assumptions such as the thin lens approximation, which should create discrepancies within the data. However, none of these were seen, which is quite interesting. And as well as referring to the experimental apparatus, multiple thicknesses were used, but it comes back to that thin lens approximation, which I'll bring up in the discussion, which one of the differential diffraction relationship uses to solve the equation. As a thin lens approximation was used she was actually used for the differential diffraction equation, that would affect the results, meaning your focal length would not change directly as plotted by that theoretical relationship, so the actual experimental data would have some divergence from the theoretical curve as the gap or the thickness of your soy sauce changes, and that's something I would like to discuss within the discussion. And also the laser itself, it wasn't specified whether it's a single mode laser, so a TEM00 laser, which only has one mode, meaning there's only, which exhibits that Gaussian profile. If it's not a single mode laser, there could be multiple modes, and that can affect the profile and also the relationships. And also the beam quality of the laser, meaning how the quality of the beam profile, and whether it actually matches an ideal Gaussian. So I'd like to go into the discussion. So I'd first like to go to your the fusion equation. Where you have any equation? Okay, all right. Yes. So this equation. So these are the assumptions you made, but you took the solution from literature, I believe.
Yes, but then the solution to this partial differential equation is found by the method of Green's function.
Yes.
If you like, I can show it.
No, that's fine. But however, the Laplace transformation here, transferring from spherical coordinates, one of the assumptions used in the solving is approximating
in this two-dimensional case, it's just affected one by half.
Yeah, so that means that would result in the z term cancelling out, which results in a thin lens approximation in this case.
For this case, I just neglect convection. So I say the temperature is evenly for every layer. There's actually for no time convection for, especially in this case, when you have two plates being very close to each other, then you have high friction at the walls, and therefore no convection takes place. Okay, this is called Bernard.
So what about your lasers? Fine if we can go to your laser and
yes.
So what type of laser did you use in this experiment?
Maybe show you myself. So this actually was a helium-neon laser, which really had a resonator and was a laser, and this to power was just a laser pointer where we manually captured the profile and found out that it really had a Gaussian TM00.
Did you measure the m-squared value of your beam to see how?
The divergence or?
Not the m-squared value of the beam. So a Gaussian beam has an m-squared value, which
I don't understand you acoustically. M is great.
Did you measure the m-squared and m is m-squared?
Maybe we're talking about some wrong definition. What is M squared? So maybe you just write down your definition of a Gaussian beam.
So this is sorry. So the m-squared of a Gaussian beam, so if it's equal to 1, it's measured experimentally from using a beam profiler. If it's 1, this is an ideal Gaussian beam. But most lasers, in fact, that are greater than 1, meaning that if you didn't measure your Gaussian beam...
For this beam, I really measured the intensity profile from the beam, and it was Gaussian, and from this beam I also did this, but I had some really slight deviations which were larger than 1 to 2%, so it isn't really...
so you think that makes sense?
There is no main difference resulting.
So your laser was a single mode laser, yes? So there's only one mode for your laser? Or both of your lasers?
What do you mean by mode? You mean coherent light of one wavelength?
Yes, but there can be multiple modes. So, for your laser. So example, was your laser...
You mean inside the laser?
Yes, the actual laser beam. Because they can be
I
clarified.
think it's called that laser. Ah, you mean
Yes.
this?
Was this your...
Yeah, it was a TNC,
Okay,
but
that's
I
good.
mentioned that.
Yeah. Okay, that's good. Because that's important because that's
Yeah,
what allows you
because otherwise
represent your laser as a Gaussian
you
beam.
maybe fix that. Otherwise, you didn't have a Gaussian intensity distribution, but in the cross section rather something like this. Or
Yeah, exactly.
and I've observed this, but I've changed the laser afterwards. So this laser were really Gaussian lasers.
Okay, that's good. Because that's important for. But in this part, you send your excitation laser onto your actual
Yes.
soy sauce. But because the laser isn't perpendicular to the
Are you
surface.
familiar with lambda and cosine law?
No, not numbers or something.
You just say that when you have a ray entering a sample under an angle of alpha, let's say, the intensity is just proportional to this cosine of this angle.
Okay, so did you take this into account in your results? Do you have a slide that represents how you took this into account, this
I know,
angle?
but you just the incoming intensity I0, and then you have to take the cosine of the length and the angle.
Okay, so
I don't really need the slide because it's just a fact.
alright, no problem. So I'd like to also discuss. So back to the idea of the m-squared value, because you didn't measure the m-squared value, but your results, if you go something with your results of the focal length,
This last round,
focal length was time.
I focus on time, it's maybe the last product. Sean, you're right.
Yes, so there's some. So you measured the focal length by moving the camera, yes?
Yeah, yes.
Yeah. So you moved the camera. How did you move your camera in sync with this time? So as each
moment, a question, why do I have to move my camera in sync? Because you can measure the ray cross-section or the ray thickness at your sample, and then you can measure the ray cross-section right here, and per time it just evolves and gets larger. And then you can measure this getting larger and make this linear propagation, which are verified experimentally.
and then you use that to determine the focal length.
Yes, and it is also the way they determine the focal length and the derivation of this one. So they choose a terminal length, which is quite appropriate for 200 microns soy sauce.
Yes, I'd like to discuss, why do you think the focal length eventually starts to asymptote out as the time goes on?
If you look at the formula, just have this.
No, but why is that, like the physics properties, why is the focal length balancing out?
Because you have your heat distribution, maybe I'll show you, because I have also an animation for this. You can see that this temperature gradient right here is temperatures, and as mentioned, the temperature gradient is the reason for the phase shift in the plate. So you have a high temperature.
Yes, no, that's true, but why, what's the actual physics behind it, rather than
You get a
the
temperature equilibrium.
Oh, the temperature
your temperature
equilibrium?
distribution.
Yeah, that's good, I agree. So I'd like to go back to your qualitative understanding of the thermal lens.
That's a drawing. Yeah.
So you bring in you talk about how a high temperature results in a lower refractive index. Why is that the case? Physics, the physical properties. Why is that?
You have the sample, and when the sample is getting heated, it expands, and therefore you're losing the density, and therefore the light could somehow easier moves.
No, I agree, but I think the important thing here is the refractive index is proportional to the density.
It's just the Taylor series expansion to the
Yes,
first order, so it isn't valid.
Why did you only take the, I understand it's a Taylor series expansion,
Because you see my temperature gradient or my temperature change due to the laser right here, and it is about a tenth of a Kelvin.
Yeah, I agree, that's good, because the second order would be another
Yes,
four magnitude
it wouldn't
difference.
be necessary.
But yeah, I think with this part, they need to be like the qualitative understanding here is also because the temperature changes the density because of the expansion of the material.
Yes.
And because it's proportional to the refractive index, that results in this distribution. I think that wasn't brought up as much rather than the equation.
Okay, yeah, sure.
That would explain more of an intuitive understanding to someone that won't understand the thermal lens effect. So I think that's essential.
I'm sorry.
Yeah, no, that's good. I just need to understand that part. So I'd also like to bring up. Oh, when do you go back to your apparatus diagram, please? Apparatus, like your experimentals. Experimentals episode.
I'm confused about the diagram.
I'm sorry. So you had a clamp here, yes?
This clamp, yes.
Yes. Are you aware of thermoelastic effects or say
So
straining the material?
you can see first of all for liquid your thermal expansion coefficient is really small.
But what about the actual of the plastic plate here?
When you have maybe
When there's strain in the material, you'll understand the
when
refractive
you
index
have
changes.
this glass, and when you now take just a ray coming in, can you draw how this passes the glass?
Just goes through.
Yes, and therefore,
But as there's a clamp here,
which what?
this clamp is pressing on to hold it together, and that results in a strain within the material, and there in fact is a change in refractive index based on the strain
which
within the material.
it remained the glass.
The glass itself here.
Yeah, but the clamp was positioned on the wall of the glass.
No, because it is holding it together
So
inside.
I don't think this effect is really important.
Okay, well, it's a way of understanding is when you hold onto something, you can see some of the
Yeah, you mean as stress objects, excuse me.
yes, stress optics, but that's what it's creating stress within the plastic itself.
But in my case, you can also just let the laser pass through without any fluid, and you cannot see any.
So you think there's no stress involved in the plastic?
I don't say not any, but at least the magnitude of all the results of this effect isn't really
Well, so
important.
why do you think the stress is not important here?
Because it's the effects of the stress are very low compared to the effects of the thermal.
Were you able to quantify some of the stress within the material due to your clamp?
No, it's quite hard, but my theory fits my measurement quite well.
Okay, that's good. So, also, in regards to finding your DNDT value for soy sauce, so the change in refractive index, you found it using literature, yes?
Firstly, I've used literature. On the other hand, there's a professor at my university which made me able to actually look up.
Do you believe that DNDT is a constant value for, say, the soy sauce across the temperature distribution? Is it a constant?
It's a linearization, so it might look different for larger temperature
Did
gradients.
you take that into account for your
I thought I've answered this question already. My temperature grade or
It's too low.
my total temperature gradient is too low to break free of this linearized model. So for this 0.1 Kelvin of difference I'll be making, the linearized
Sorry,
Similar.
the equation
I agree with that, yeah.
stop there, that was awesome, and you put your comment for summary. Well, yeah. Do you want to-
Yes, the reporter was able to use a lot of mathematical models, either derived by himself or as well as theory, to present the relationships of the thermal lens in terms of lots of factors, and due to that, they're able to measure the focal length of the lens. However, I think there were some assumptions taken into account in the past literature, and as well as the mathematics, such as the strain of the material, which actually does in fact affect the refractive index due to the strain, as well as a thin lens approximation, which, so when varying the actual gap of soy sauce, if you assume it's a thin lens, the distance of the actual soy sauce shouldn't affect anything, but in fact it was shown here to affect, whereas it was taken as a thin lens, which doesn't make sense. But the discussion overall, though, we talked about the factors, and that really came in together, and how we discussed the trends, and I think the report really good job.
Thank you very much, well done. Let's pause and have a round of applause. So, we've had, sorry, we've got to lose track. Questions of the reviewer to the reporter and the opponent.
Good afternoon, my name is Jakub Szczawina. I'm going to review this task. Firstly, I would like to ask you to turn on slide 18.
Or the right.
Okay, so we can see here that the time of development of the thermal length is around 10 seconds. You can now slide. Could you turn on slide 11?
I mean the temperature distribution.
Yeah, you state here that it developed in 10 seconds.
It is not the, maybe you know before it is not the absolute temperature which causes the lens, but it's the temperature gradient because.
Okay, yes, I see. So it,
and you can see that this establishes fairly quickly, so it's really quickly established. And
okay, but we here can see the times up to 99 seconds,
yes.
Which is in minutes, and you state that the thermal lens develops in seconds. So could you elaborate on that?
That's right, because you have a growth of the absolute value of the temperature. But if you look at this slope, at the gradient of your change, which is important for the phase shift, because the phase shift is relative to this point.
Okay, thank you. Were you able to measure the thermal diffusivity of the...
thermal diffusivity, yeah, I've determined...
Because it affects the temperature.
So the thermal diffusivity is defined as follows: the thermal conductivity divided by the density and the specific heat capacity. And the thermal conductivity itself was obtained by literature from this handbook. And the specific...
Okay, thank you. You stated that it is always a diverging lens.
Is not this always. You can just go behind the focus and then give.
Okay, so this is really how it was, because in the beginning of your presentation you stated. Okay. Thank you.
You just have the laws of geometric optics.
Oh, okay. Thank you. Could you show us the specific value of the NBT?
Yes. All right.
Okay, you are stating that the coefficient should be negative, n goes down, but here it is clearly, it is positive.
Maybe I don't understand it properly.
Yeah, here it has positive value, but it should go down. So.
What should go down?
Well, the refractive index with temperature.
Goes down.
Okay, but there is positive gradient. Their version.
Are you confused with the signs?
Sorry, we're out of time.
Statement. So, firstly, in the report, we have seen a presentation of the experimental setup they used. Next, they moved on to more of a qualitative explanation, which we believe lacked core physical intuitions. Then they were dealing with the refractive index changing with temperature gradient, and we were confused by that value, but now we can see that, that there is a negative sign in the actual expression. Well, then they presented more of quantitative theory based on heat equation, and then they compared it with their experiments. We liked that they measured the absorption spectrum of the soy source, and they provided some quantitative theory, but it was all based on the literature, and we lacked their own contribution in this part. They have presented apparatus, and they elaborated in the beginning on different concentrations of soy sauce, which we liked. To the cons of this, they have shown that they can change the width of the sample, but did not elaborate on that further. Also, They did not explain why precisely should we use 200 micrometers of soy sauce and why to use even soy sauce. Then to the opponent, we like his questions on focal length, its measurement, and so on. He pointed the assumptions were not stated or in satisfactory way explained, and he also asks about the modes which we liked. He pointed out the strain and its effect on the optics, but we believe this is irrelevant and he spent much time using this. He did not use his questions that effectively. Also, he stated about the angle. So, stated about the excitation angle, some things we don't agree with. Then, the laser properties were further discussed in the discussion. Focal length measurement as well, which was cleared out and that we liked. And also thermal lens effect included explanation. They did more into this, and we believe that we arrived at some conclusion, but it was not that satisfactory. That they were clashing on the effect of the thin lens approximation. We believe this is valid because really we are using only thin films of soy sauce, and the reporter was asking, the opponent was asking if it is a valid approximation. The reporter said it indeed is. Then they were asking about, the opponent was asking about the strain effect the thermal lens might induce, and the reporter stated it is not something we should worry about, and we believe it is insignificant. Thank you.
So we now have the 2 minutes, then reporter, yeah, 2 minutes.
So maybe I've been accused from the reviewer that my temperature distribution is wrong, but I think it just missed out on the sign here. And then for the thin lens approximation, there was claimed that it's not valid, but for 200 micrometers in such small temperature changes, it is valid. Furthermore, the qualitative explanation, I thought it was quite clear, because when you have liquid which gets warmer, it expands, and therefore you get a larger volume for a lower mass, and you have increase of temperature, decrease of density. And this induces that the refractive index behaves like it does, and therefore, yeah, it's just some basic physics. I thought that were clear. Anyway, now also I've been accused what happens when I put my focal length above or behind the focus, but I can clearly say that then it's just a thing of geometrical optics, and one can easily go for the thing that happens by writing down the relevant measurements. And then the final experimental thing that wasn't quite clear, I think, is my assumption of a Gaussian beam, but therefore I tracked the radial resolved intensity profiles of my laser and fitted a Gaussian through it, so they were actually Gaussian beams. Thank you.
So now we move on to questions of the jury. Yes.
This is for Angad.
Yes.
So you did mention like stress or strain effects. How do you think, not considering the stress or strain effects, how do you think that affected his estimate of the focal length?
So when you have, say, stress or strain on, say, the material, there's a change in refractive index due to the internal strain forces, and because of that, you the beam wouldn't actually go through from one end to the other. Because of there's a change in refractive index due to the strain, it could diverge a bit or converge depending on the strain and its properties. And due to that, the Gaussian beam profile detected at the camera wouldn't be only because of the thermal lens, it's also because of the strain effect on the actual plastic itself. When we're trying to consider the plastic negligible in the effect, in fact, the strain would disrupt this. It could potentially disrupt it. That's why I questioned the reporter on whether they considered it and why they think it is an effect in this situation.
So can I just ask one quick thing?
No.
Oh, no.
No.
Yeah, but the question again is, on the overall phenomena, how relevant is what you're saying? In terms of the phenomena,
On the actual,
thermal lens effect.
the thermal lens will still be viewed, yes, I agree with that. The thermal lens will still be viewed, it would just be maybe some discrepancies either in the focal length of the...
How big is those discrepancies? Are those relevant from the point of view for the final result?
No, I think I agree as well with the report that they would be quite small. But it actually does also depend on how tight the clamp is. But I imagine the reporter took the intuitive sense to not tighten the clamp to, say, put stress on the material. So I 100% agree. And some of those error bars might also be due to some of the small...
Let's move on to some other questions.
Sorry.
Can you just briefly clarify the results that you show us? They are all for the same thickness, or you show us something for different?
Yes, they're all for the same thickness,
Of 200 microns?
200 microns.
Thank you.
But you can vary the distance and then you get a linear trend because you get a high absorbance.
And can I also have a very brief question for the opponent? Can you briefly tell us what you mean by M-squared?
So M squared measures the quality of the Gaussian beam of the laser. So M squared 1 because it follows the exact ideal Gaussian beam. But when the value of M squared for the beam, it's measured through beam profiling processes.
Okay, thanks.
Oh, okay.
On slide 9 for the thermal conductivity of the soy sauce,
Yes.
did you measure that or you
So the thermal conductivity
of the soy sauce?
and
Or the absorption coefficiency?
the
I'm sorry.
absorption coefficient,
Uh-huh.
it's been measured right here using the spectrometer. So you have the absorption coefficient corresponding to the volume
Okay.
fraction and then you have lambda.
Thank you, thank you.
So on your slide number 10, and you keep the correction, you have quantity Q in, and there is now this quantity in following formulas you derived from this equation.
What do you mean?
So in following formulas and further formulas, there is no
You mean the absorbance?
yes.
It's in the heat flux right here.
So
Because you can
and
use...
where is this heat flux in the formulas, for example, on slide 11?
Yes? Well, slide 11. Okay.
Okay, compare slide 10 and 11.
Yes?
Slide 10 you have, so where is Q here? It should be here.
You're looking for the Q which flows in the heat flux in the center. So it is actually considered in those parameters the magnitude of the heat flux for the infinite time scales. Or I don't really know what you... Because this is the solution to the equation with considered Q.
And I think I could say that the Q is really a function, it is not just one parameter.
The Q function is actually related to the intensity of the Gaussian
Here you
beam.
can see it.
Yes.
So for the reporter, you mentioned that the dN by dt is linear, right?
Is
Linear.
yes.
How do you find that out?
So it's stated in the literature that the refractive index behaves linear for a small or for a variation, or everything behaves linear for small variations,
Okay.
and therefore I assume that my temperature change is just small enough to be linear.
Okay, so for the reviewer, you agree with the reporter on that?
Well, on the fact that in small regions it is linear, yes.
How about
For
the
the other
other
time.
Just what, just then, yes or no? He
Are
agreed.
you talking about DNDT, sorry? I think there's a terminology issue. DNDT is a constant between small temperatures, meaning DNDT doesn't change because it represents the gradient between N and N temperature.
Okay, thank you very much. My score is, we're going slow now, 6, and an 8, and a 7, and a 7, and a 7. And the opposition, I am giving it also a 6, and a 6, 6, 7, 6. And the review, goes back here, giving it an 8, and a 5, and a 7, and a 6, and a 5. Disagree? No, that's cool. So we've got an 8 in the report. Would you like to say, would you like to go to it?
Yeah. I think it was really nice presentation. I think you really led us through the terminology, your setup, like theory that was like really nicely explained and detailed. I like also how like you showed us all the comparison with theory and experiment. That was really good. I also really like how you act in discussion, where you added some new physical insights, which we really appreciate. So yeah, that resulted in like 7.5 from my side, which I swing to 8.
Like I give a low score, because I just kept writing, why soy sauce? What's in soy sauce? We didn't ever
It's
get
stayed into the task.
So, anyway, I would have liked to have found out a bit more about what was actually going on with light hitting soy sauce and what's in soy sauce and things like that. I just felt that was a bit lacking, so it just pulled you down a little bit. Yeah, and there was a few things that I felt didn't communicate to me as well. There's a communication, there's a few things I didn't quite understand, and it's not my field particularly. So anyway, that just pulled it down a little bit, but it was pretty good. Moving on to the opposition, we all pretty agreed there. So Vishuki gave it 7.
Yeah, I'll explain. So, first of all, I really like your questions. So it's 1 and 12. Then I like your speech. So it was, from my point of view, it was all that should be mentioned, mostly mentioned, and what you, in your style, what you focus was good. So it's 2.5 for opposition. Discussion was not exhibit or raise something new. So I want to maybe from you to mostly to discuss more the angle between these two bases and their influence on this. So I give you 2 points of discussion, and this is
And somebody would like to talk about the 6 one?
Yeah, 6, negative 6. I think you made some relevant points and some that were not so relevant from the point of view that I kind of doubted with you during the discussion. So I wish you would have concentrated more on the relevant points, especially when you tackle the discussion on the density, you know, the relationship between density and the thermal factor. That was a good point, but you didn't push through. And so that's why I gave you a little response.
And last of all, the review. I gave it the high score, partly because you mentioned soy sauce and that they had soy sauce when you mentioned that it wasn't enough. But otherwise, I just thought it was very well done. You just kind of just got good. You used the time well on the questions, and I thought you reviewed the parts of it very nicely. It's a bit of an issue with boxes not being filled in, but that was, but mostly it was pretty good. Yeah. And you gave it
I got 7.
So you were talking about that?
Actually, I give you 5.5, but I can't round it out. The part that I give you the lowest is the question asked. I think you didn't ask that much question, and the opponent didn't have any chance to answer anything. I think that the part that I got the lowest score for your role as a reviewer, and I think you didn't analyze a lot of the discussion in terms of physics behind it that much. So that's my 5 score.
So, 7?
Yeah, we've given the highs and lows and the
Yeah,
three.
which is the highest?
Yeah.
Oh, sure.
Yeah,
Okay.
the mine was 8. And
I
the
would
other-
like to, if I can, to comment all three. The reviewer, I give a 7 because I think they pick up points in the discussion, especially being pointed some pitfall of the points. It's a pitfall of the presentation. Again, the intuitive physics was missing. And again, consistently with the 5 before, that's why I think I invite all of you to just concentrate on the physics. You know, the formula and the experiment are important, but the physics are intricate. And they pointed out, those are the opponent, but also they pointed out how the opponent did not push through the relevant question. I think it was a good review from that view.
Okay.
Can I say one really quick thing? I really enjoyed the discussion between the reporter and the opponent. I felt that you guys were learning from each other, and I think that's what today's all really about. And I really liked that.
So well done. We've got a 10-minute break. It's on the clock. Yeah, so we need to now. Well, let's just do